So, in the last class, we studied about the basic CNN architecture. We learned about filters, also known as kernels. We learned about something known as convolution. We learned about how we can extract features using convolutions. And what I mentioned that in the next class we will be learning about something known as pooling. But before that, let me explain you a few things, and just let's get revised over the whole concept one more time. So we knew about the edge detection, right? And we knew how Sobel edge detectors were used to identify the edges, and we know that edges can be used as one of the features. So we had a structure like this firstly, then it was convolved with filters. We had 3-dimensional filters, if you remember very well. We had these because our images are 3-dimensional, right? We have RGB images, so we need 3-dimensional filters to actually solve these RGB images. So what would happen was that for each image, the red channel would convolve with the red channel of the filter, then the green channel will convolve with the green channel of the filter, and so on. So you would get the idea. However, the output was a 2-dimensional output, right? Then what we used to do, instead of using just one filter every time, we were using multiple filters, right? And that is how we were getting it. So we are getting now output here. Since I have used 2 filters, so the final dimension will be 2. So that means we are getting 2 outputs or 2 features. They are not exactly called features, they are known as feature maps. So I mentioned features so that it is easier to understand, but now we will be calling those as feature maps. So we are getting 2 feature maps. Each feature, number of feature maps is equal to number of filters. So the number of filters you will be using, that many number of features you will be extracting, hence that many number of feature maps, right? But it does not end there. If you remember, in our MLP also, we first had the summation, right? We had the weights with the x's and all, we had the summation. Then this was followed by what was known as an activation function. So here in the same way we will be having an activation. Usually for convolution we use ReLU as an activation function. The reason why is it is easier to understand using that. So once you get that, you have this ReLU over the weights plus bias in this. So if you remember, you had this, and y was equal to summation of all wxi plus b, right? It was summation of the whole thing. So this whole thing is there. Now you will ReLU over the whole thing. ReLU is easier to do even in CNN. The reason why is ReLU is basically just maximum of 0, z. So whichever is maximum, either 0 or the number itself, the value itself will be kept, else it will not be kept. So that is it. So you have a convolution layer, if you remember. Let's just go over it one more time. So you first have a convolution thing where the image is here, and then you keep filters over it one by one. Then you have something known as stride, which tells you how many pixels you have to skip over, and then you have something known as padding. There are 2 types of padding: valid padding and same padding. Same padding means the input size should be equal to the output size. So that is how accordingly the model will understand and pad. And then we have valid padding, that means no padding. And then we also had this formula. So what was the formula? So the result is equal to n plus 2p minus f by s plus 1, right? So this was how the whole thing was decided, what will be the dimension of the result. So now, and instead of using one filter every time, we will be using multiple filters. So there will be multiple filters, and the output will be equal to the output dimension will be equal to this number of filters. So once that has been calculated, so this is basically the calculation of the weights and the addition of the bias. We will pass this to an activation function value and we'll get the output, right? So this is the whole structure, if you will understand, I spoke about in this manner. So we have the inputs here. So now we have finally talked about the entire neuron structure. Now what we will understand is how we form this layers kind of structure, in and out and in and out, right? Now we will be discussing about such stuff. Okay, so this is a very nice image, basically the structure of a convolution. So if you talk about CNNs, convolution neural network, this is how they actually look like. Here we have an MNIST data set as an input, and now we will understand what is happening, right, one by one. So first it says we have convolution 1, 5x5 kernel we are using, and valid padding we are using. So we have an input size of 28x28x1. This one is basically because the number of channels is equal to 1 here, okay, because this is a black and white image and not an RGB image. So what will be so if it had been, let's say, into 3, if this had been a colored image, we would also have into 3 here in the kernel size, right? So but since it is not, we will not be considering this. So we have this. So now the shape, resultant shape, if we have to calculate, what will that be like? 28 minus 5 plus 2p, but since this is valid padding, so the padding is 0 divided by the stride. It's not given, so it's basically 1 if it's not given, plus 1, okay. So this whole thing comes out to be 28 minus 5, 23, 23 by 1, 23, 23 plus 1, 24. So you can see 24, and the number of channels or the number of filters is n1 filters, hence this is equal to n1. This is 24, the height is 24, the width is 24, and this thickness is n1, right? Then we have what is known as a max pooling. So what exactly is max pooling? So we will be talking about that now, okay. So let us get back to this particular image that we understood, right? We talked about this, and then we knew how this was calculated, and we were getting this outputs, right, the result and everything. So first let us talk about why do we need max pooling, or we'll talk about what max pooling is obviously, but let us talk about one of the problems that we have with convolution, right? So why max pooling, or any kind of pooling? Basically what pooling does is basically reduce the dimensions, okay. So why do we exactly need to reduce dimensions is our question right now. So let us talk about how much it is required to calculate for this particular cell, let's say, okay. So we require, how many multiplications are required, that is required. So we have 3 cross 3, okay. So 3 cross 3 is the multiplications required to calculate a particular cell. Why 3 cross 3? Because we have 3 cross 3 as the size of our filter. So this 3 cross 3 will be multiplied to all the 3 cross 3 in this area, hence we will be having 3 cross 3 multiplications to find one result, but we have a result of 4 cross 4, so into 4 cross 4. But okay, this does not seem like a lot right now, but think about this 4 cross 4. Now we do not use just one, so this here is a one dimension, so this is a black and white image, right? But we also have RGB channels, so for RGB this is equal to into 3, because for each channel you have to do this, right? Okay, but we do not have just one filter, we have more than one filters, right? So let's say number of filters are usually equal to 2 to the power something, right? So let's say we have 32 filters, 32 features, okay, enough. I mean it is pretty less, but alright. So into 32, but then again that is just for a single convolution layer. We have multiple convolution layers, right? So if let's say I'm using 3 convolution layers, so you have again into 3. Now again it's still not a lot, it's very easy for a computer, but then where is the problem again? Look at this, the input is 6 cross 6. I mean you are not going to find any image that is 6 cross 6. Even the easiest data set, that is the MNIST data set, has 28 cross 28, right? So this whole thing changes. So you are not going to get a 4 cross 4. In fact, if you remember, this was coming out, the result was coming out to be 24 cross 24. So instead of 4 cross 4, this will be 24 cross 24. Now is it feeling like a lot? Yes, because this is actually a lot, and this is like the easiest one, and it keeps on increasing. So right now I'm just using 32. This is the smallest that you are going to get. So it is going to increase and increase, and yeah, it's going to be very hard. Plus I have not even added padding. If I add the padding to as same, the resultant size increases. So in that case, this is going to be very big. So this is going to be, instead of 24, this will be 28. So this just keeps on increasing. If you will look into it, you will realize it just keeps on increasing, massive increase. And even now you have cameras and videos of like 4K quality. So 4K is like 1080p, maybe more than 1080p, 2160p. This is actually a lot to calculate for a convolution itself. And it's just not one layer, it's more than one layer. Your laptop is going to hang, it's going to lag back, the RAM, it's going to use a lot of the resources. So it is not possibly feasible. That is why we have the concept of pooling. So what pooling does is basically, it reduces the dimensions. It reduces the dimensions without actually losing all the important information in an image. So let's suppose I have this image, the whole thing is background. Here let's say I have a table. So I'm very bad at drawing, so you have to consider that. So here you have a table, right? And the whole thing is background. So I know for a fact this part is going to be important. Not everything in the image is important, but we still have to convolute the whole thing. Hence we have the concept of pooling. So what actually happens in pooling? So pooling itself is of two types. We have max pooling and we have average pooling. So what max pooling does is basically you have to define or decide how much you want to reduce. Okay, so this is an image, an original image, and I am going to reduce the size. So in that case what I will do is I will do max pooling. So what happens in max pooling is it takes nearest neighbors of a particular number. So you have 4 here, all the nearest neighbors 9, 6, 5, okay, and we find the largest pixel value and we keep it. The rest is all discarded. In the same way here we have the largest value of 5, so 5 is taken, the rest is discarded. In the same way we have 6 here, that is taken and the rest discarded, and 8. Okay, and in the same way as the name suggests, we have average pooling. What average pooling does is basically it takes the average of all the 4 points and you get the value. In the same way for the other 4, and so on. So what happens is there is also one more known as minimum pooling. So this basically takes the minimum value. You can understand that. So what happens basically is it takes the most important pixel or the high pixel with the highest value. That is what this max pooling focuses on. Here average pooling, all the pixels are given equal weightage. So now let us look into the structure once again. So we now have convolution, we understood this part, then we have max pooling, right? So max pooling, what happened? The size is reduced by half in max pooling because the max pooling is 2 cross 2. Okay, so what that means is if you look here, what will happen is you will need a 2 cross 2 as your reference, frame reference. So that is why every 2 cross 2 will be selected and you will find the maximum value here. So if your max pooling is 2 cross 2, that means 4 pixels will be selected here and maximum of this will be used. 4 pixels as in 2 in the length and 2 in the breadth, and that is how it will go on. So in the same way here you have max pooling, so 8 cross 8 you will take 4 pixels here, it's 2 pixels as length and 2 as width, right? And then you will calculate the value. So what will happen is since the max pooling is 2 by 2, it reduces the dimension by half. So 24 cross n1 will become 12 cross n1. Then again we will do another convolution on this. This is a 5 cross 5 kernel. Again we will be using the padding is valid, so no padding basically. So how will you get the outputs as? So you have 12 minus 5, no padding, so 0 divided by stride is 1 plus 1. So this is equal to what? This is equal to 8. So you get the output 8. Then again you have max pooling here 2 cross 2. This number will be reciprocated to give the output. So that means if you have 2 cross 2 as the max pooling, the output will be by 2 and by 2. So you have 4 cross 4 and you get the output. Now the final thing is they have flattened it. You might remember I talked about flattened earlier. You have the MNIST data set and you flattened it into a one-dimensional thing. And once it has been flattened, it is passed through all these neurons, right? Neural networks, neural layers. So it is passed through one. This is an hidden layer obviously, and once this is passed, we pass it through the final. I think this is the softmax layer here. So it is passed through a softmax layer. How many number of neurons will be there? 10 neurons, because we need the output of 0 to 9. So this is a basic structure of a convolution neural network. Now there are different case studies and different ways in which neural networks are used. So by that what I mean is, sometimes here this is the basic design for 28 cross 28. I can change this obviously, and instead of say valid, I can use same padding. So I am going to get different results. So since there are so many possibilities when it comes to actually understanding about neural networks and convolution neural networks especially, and you can put anything anywhere and it just becomes a bit difficult. So we actually have case studies and different structures of neural networks that have been proven and that work well for every case. So in that case we will be understanding about those, and then we will understand about something known as transfer learning as well. So this is it for now. Thank you and keep learning.